Okay, so obviously these ones we started off with were simpler examples, but I think this example would be something that I would actually use in production. Okay, so you can see that there are more nodes, but you can also get a sense for like how much more powerful that a group of nodes could give you, and provided they're plugged in the right order and stuff. It's not that many more nodes that you'd really have to set up a complete system with. I've seen nodes and built networks that were thousands of nodes. So, if you have to, one of the more involved projects I did in the last few weeks or months was I had to simulate a forest. So that was probably about 150 trees with all kinds of characters running through them and branches breaking and millions of leaves, and each tree had to react to the characters, and all kinds of stuff had to break. So that did take thousands of nodes to do it. Also, I had to generate bones on the fly to deform high-res meshes for the trees and stuff. So if you think about a system like this, and they can be contained very well. Like if you just open up the scene, it would still look sane. It wouldn't be like you can collapse these things. So like if I wanted to make this all in one thing, like say maybe just with the brick and the input, and I wanted to simplify it, I would do something like this. Okay, and that for just looking at it the next day, you're like, what did I do? Well, at least the next day you don't have to remember everything you did, but you could know enough to like say, okay, well, instead of a circle, I want like, let's see, what do we want here? I want like a triangle. Okay, and then I get my maybe that didn't work out too well, did it? I want my triangle bricks instead. Okay, so you don't have to remember everything you did. It's all just in here. I can forget about it if I want to. So that's one of the good things about Houdini's hierarchical structure, is that you work for a month, you forgot completely what you did a month ago, but you know what goes into it on this side, you know what goes into it on this side. For instance, the sphere. And you can kind of say, okay, well, I've established that works, so let's get the rest of the things that need to be done. Okay? However, we do want to understand what's going on in that network for today. There we go. All right, so let me show you guys what's going on here. We'll see how much time we have to do parts ourselves. Okay, so I started with a curve. I like curves. Houdini has some pretty cool curve features. They're really good also for wire simulations. I love Houdini for wire simulations. So simulate fishtails and trees and all kinds of other stuff. They're pretty fun. Wire simulation, yeah. Like hair. You could put like a bunch of wires on someone's head and have the hair jiggle. Yeah. So. Okay, so here's a curve. We make a new curve. I'm just gonna let's do like curve. There we go. Okay, so now this, we actually do have to use the viewport. So I know we've been working all in this, but a curve is fairly interactive. We wouldn't want to like type in the number values here. So here I'm going to click on the node. I'm going to go to my viewport and hit enter. And what that does is it says, okay, I actually want to manipulate this node in the viewport. And some nodes have handles. If it doesn't have a handle, you just won't be able to do anything. But if it does have a handle, then you'll be able to manipulate it here. Okay, so I'm going to draw a curve. There we go. All right, and if you want to manipulate your curve from there, you can just click on stuff. If I escape out of it, escape key, then it's done. If I want to go back and do it some more, enter again, and do some more. Okay, so in that respect, it is like a editing mesh or whatever. Okay. Okay, now I'm not too happy with this curve, so I want to smooth it out. So after that, I'm just going to do a smooth sub. Now that smooths it way too much, okay? So here's the smoothing iterations up here. I'm just going to do like maybe 1 or 2 iterations for smoothing. So just enough to take the edge off, make sure there isn't like this jaggedy lines in there. Okay, now one problem with this line is that these, if I were to copy bricks onto this right now, let's see, where's my brick? Okay. Okay, now, first of all, they're the wrong orientation. We'll get to that. But the second thing about this curve is these point positions have absolutely no relevance to how far apart these bricks should be, right? Okay, so who suggested doing an expression for that earlier as to the length of copies? I know it was somebody. Like, why? Ah, yes. Okay. So the question was, when we were actually manually moving over the copies, why don't we do an expression for that? Well, here's where you would do an expression for that. It's when you have to be procedural. You don't know what you're going to get coming into the input. So unless you want to space apart vertices for half your day for a few weeks while you design your castle, you want to have an expression to say, okay, this is how long this segment should be, this is how long this segment should be, this is how long this segment should be. Okay? So on this line here, these vertices are clearly too far apart. I'm going to resample that. So that's pretty handy. Resample node there. Okay, and it resampled it. Now let's see what happens. Okay, well not only are they the wrong orientation, but they're way too close together, right? So what do we do? Well, we need this length to change based on how big what is.
Width of the brick.
Yeah, we want to figure out the width of the brick, right? Okay. So in this resample, it has the length right here, and you can see it that my vertices are increasing or decreasing. I want this to be the length of the brick, so I would actually query this brick geometry. Okay. So we want to get this length of the brick. This would be the z-axis, I believe, of the brick. How do you tell? Well, I'm looking at this little blue guy down here, but there should actually be a guide. I hit D, by the way. They changed it around in 12. I don't know where it is right now. Origin nomen. Okay, so if you want to know where you are in world space, there should be an origin nomen that appears. I'm not. Oh, there it is. Okay. Okay. So there's the z-axis. Okay. So we want to know how far apart are these two things, because we don't know what we're going to take in. We don't know if they're going to change the size of the brick. We don't know if they're going to replace the brick with a stone. You never know. Okay. So in my length here, I'm going to use the bounding box expression. This is one of those expressions like the rand, like the stamp, that you will use all the time. Okay? So, ebox. Third expression for today, I believe. Now, it has the string surface node, and then it has the float type. Okay, so I want a string which is in quotes, merge brick. See, that's going to there then. All right. Now I want the type. Now, in our bounding box, it actually works. It's probably was invented at the same time prisms was invented. So it works in a very old school sort of way. It works actually different than the other expressions do now. So if I type in bbox, notice it has these entries here, and that's just what you put in to get what you want. This is a very, very old expression. Okay. So in this case, I want the size of z, this guy. Okay, so that would be dz size. Okay. All right. So do that, and then I do without quotes, and this is the weird part about it. So No way to get around it. It's weird. Sorry, guys. DZ size. And that gave me a number. It gave me the brick's length of Z. So now all of these are spaced approximately how far apart our brick is. It's not going to be perfect. There's other more advanced things we could do, but for this example, that works out pretty well. I'll just rotate this guy just to show you guys that it is in fact close. Okay, so you can see that's close. We want to find out a better way to do that rotation a little bit, but yeah, it's close. Okay. Okay. Now we've got these evenly spaced, but what to do about that rotation? We want the bricks to actually be facing each other, right? Like we want them to go in that kind of snake-like pattern. So for this, we have to talk about like matrices and normals and up vectors and things like that. Has anyone had any previous experience with like what a transform matrix is? No?
Houdini or just
Anything.
Yeah, we work with that in the
Great. Yeah, so like a transform matrix, it's basically like an axis, right? And to build that axis, it needs to know kind of like its position and its rotation and its scale. Okay? So when you use the copy SOP, you can put that information in that right input, and they will orient themselves to that axis. Okay? And the easiest way to do that is just with the normals. So if I take these points and I give these guys some normals, so add normal with my point SOP. Okay, now to see the normals, we click on this little guy. Okay, so now I've got normals facing this way. Look what happens to my copy there. See, they're all oriented that way now. Okay, so as I adjust these, now they should be 45 degrees once I put this in. Okay, so it's actually orienting the copy towards the normal. It's like a look at. Okay? Now, if you wanted to get really fancy, we could put in an up vector here as well, and that gives it an extra axis of stabilization, but we don't really need that for bricks. Okay, but here's the up vector in case you guys are curious. Okay, so how do we get these normals to, we don't want them to all go in one direction. We actually want them to like go to each next segment. Okay, so for that, I'm doing a little bit of trickery. Okay, so first I'm just going to delete the line and keep the points. This is just for simplicity's sake. You don't have to do this, but it's easier to look at. So I'm going to use a delete SOP, and I'm going to say delete everything with a star. Okay, so it deleted everything. Now there's 0 anything. That doesn't do us any good. We actually want to keep the points though. Okay, so there's delete everything but keep the points. That just got rid of the line. We just have plain old points now. Okay. And now each of these points have a number associated with them. 0, 1, 2, 3, 4, 5. So I need to come up with a way to get this point's position and get this point's position and then subtract those two positions so that I have a vector that looks from here to here. Does that make sense? Anybody had to do anything like that? Yeah. Okay, I'll show it in 2 points then. Okay, so I'm going to do an add. This is just a side example here. Okay, so this gave me a point at the origin. All right, and let's just move it around. I'll just move it like, I'll move it over here. Okay, now I'll do another add. somewhere else. Okay, so now I've got add number 1 over here, add number 2 over here. Okay, so we want the normal of this point to face that other point. So for that, I'm going to do a point sop. And it has a second input for that very reason. Not just this, but so you can do math between different sets of points. That's why the point sop is very powerful. Okay. So I'm going to say add normal. So it's going to be the position of this guy, sorry, actually the position of this guy minus the position of this guy. And that's going to give us a vector representing, the trajectory there. Okay. So the local variable for position is, and we can see it up here as well. I'm just going to show you how I would find it out if I didn't know. Tx, Ty, Tz, local variables on the help card, point position. Okay. Now each thing in the point sop can have Tx, or for instance Tx2 would be the second input. Okay. So Tx2 minus Tx. There we go. Okay, so that's adding that normal. Okay, can't really see it yet, but okay. Oh, that's because I didn't put it in the normal. Duh. I put it in the position. My bad. Okay. Normals. Tx2 minus Tx. There we go. So you can see our normals starting to form here. Okay, so that's the x. For y, what do we need? Yeah. Okay, so we need ty2 minus ty. So the look at position minus the current position. Okay, and then z. There we go. So looking at this guy, we can see that it goes, this vector now goes from this to this. Okay, that's the direction we want. Now that's just for one brick though. So how do we get it for all the things on that curve? Okay. So, okay, I've got all these points, and to make things more complicated, it's the same geometry, so I can't like do the current point position because it's itself, it's not something else. Well, we're going to do a sort, and by sorting, we're just going to offset the point number by 1, and that way we get the points going in the first input, and we get the points offset by 1 going in the second input, and then we can just do the same equation there. All right? So I'll do a sort. Oops. Sort. Okay. So you can sort these point numbers, like say we wanted to reverse them or whatever. There's just options for that. Okay, so here's that. Let's do reverse. Okay, so it reversed it. You see the point numbers changing here. Okay. So we want to do an expression for that. I want to say if the point equals the total number of points minus 1, because the number of points starts at 0, right? So then I'm just going to set it to something really big. That means it'll always go to the end. Actually, let's just simplify that. If point equals 0, if it's the first point essentially, then really big. Otherwise, point plus 1. Now that should just shift everything over by 1. Okay, so you see that here's, before I do it, it's 0, 1, 2, 3, 4. And once we do that, now it's just shifted everything over by 1, all these point numbers. If it's the first point, set it to the end. Otherwise, point number plus 1. That's the expression that we're sorting these points by. You guys lost?
Oh, yeah.
Okay. It's all right. So this kind of stuff will start to make sense.
Like I'm taking a trick.
Okay, but now so we've got point 0 on the first input for this guy. See, this is point 0, and then if I plug this next guy in, I would have point 0 here. So that means I can subtract point 0 here from point 0 here. I'll get my vector. Okay, so let's see the application of this kind of thing. Here's my points up. Go on this side with this one. Go on this side with this one. And do my normal. Same thing as before. tx2 minus tx. ty2 minus ty. tz2 minus tz. Okay. Now if we look at these normals, we can see that we have a nice even line formed by these. Let me see if I can scale it to show that. Normal, normal, normal. There we go. Scale normal. Okay, so you can kind of see how all these points are looking at each other now if they're normals. Okay, so you don't have to understand that expression we did. Just understand that we took line number 1, line number 2 offset by 1. We subtracted the positions of the 2 lines, and now we have our normals that look in that direction. Does that kind of make sense? I hope so. Okay. All right. So anyway, that's how I got the bricks to face each other. Okay. So now when we copy our bricks, it's both the right length and it's also going in the right direction. Okay. So if we change that, get a different result. Okay. And it doesn't just work for x and z. Remember, we put in ty there as well, so it'll work for y as well. All right. Let's see. Here I'm just doing some cleanup. So here I'm taking this point. Let's just plug in our curve here. You've got this one really funky normal because it doesn't have a point to go to. It's going to the very last one, right? So here I'm just killing the last point, getting rid of that. Okay. Now, who wants to take a wild guess as to how procedurally we would get the brick in between the last 2 bricks under it? Okay, so we've done our first row of bricks, but the second row, that's a little harder than just like moving it up and over because we've got a curved wall. So how do we get the bricks? They have to go in between the other 2 bricks, right? That they're below. So this would be a problem that you guys would have to figure out if you were doing this effect. The producer couldn't go up and tell you, I would like this expression to dictate how the bricks react to this scenario. You would have to come up with this solution here. That's why you get paid the big bucks. All right, so what would the solution be?
Did you offset points?
You'd offset them, but by how much?
By half of it.
Half of what?
Half the size of the brick, maybe.
Yeah, but then what happens when the curve on one side and then you curve on the other side? Wouldn't offsetting by a blanket amount, wouldn't the direction be wrong?
You'd have to bring back the math that you applied to that first one, to the other layers, applied to an offset. How that happens, I don't know.
That's pretty much it. We already had some logic worked out that we knew what direction they were going in, right? We knew how long that direction traveled. So let's not overcomplicate things. What's halfway in between this position and this position? What's that? Yeah, what is this? Is pretty easy to figure out. Half of this and this. Almost. It's just an average, right? So it's tx plus tx2 divided by 2. All right, it's an average. Okay, so here I take my my line. All right, so this is the original line. This is the line offset by 1. Okay, 1 point. Okay, so it's the same line, it's just the point number's changed. Okay, so point number there, point number just changed for that, just offset by 1, and then we do average. Okay, so tx plus tx2 divided by 2. Next one is ty divided by ty2 divided by 2. Next one is tz blah 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 divided by 2. Okay, that gives us the average position between those 2 points. Okay. And then we do the same exact operation we just did up here. We just do that again to give it the normals. All right. I'm going to move it up in y. How much should I move it up in y? The size of the brick. Awesome. Yes, the size of the brick. So we need the bounding box of y. Right? We already know how to get the bounding box of z. We just do the same thing for bounding box of y, right? So we move it up. Okay. And then we put them together. There we go. See? So now if I copy my brick onto this, alright, so I'm just going to put this in the left input, or sorry, right input. I'm going to put my brick in the left input here. See the result of the copy. There we go. So we've got our 2 rows of bricks. Okay, we had to do some basic math for it. We had to compute a vector between point A and point B to get the direction, and we had to do the average between point A and point B to get the position above it. Right? The offset of each point was the length of the brick. The height is the height of the brick. So we had 4 pieces of information that we had to turn into this procedural system. But if you really break it down, it's not that hard, is it? It's just that obviously we don't know the program, we don't know the nodes, we're very fuzzy on expressions. But in terms of actual problem solving, you can see how you'd set up an effect like this, right? Hope so. Okay. All right. So at this point, once you have this system here, it's just a simple matter of duplication. So you would once again copy it by the length of the brick in y, and that would create your bricks, your brick wall. Okay, does that make sense, everybody? Groovy. I'll show you this color trick, and I'd encourage to make them different colors. And when we wrap through this lesson, I know we won't have time to do this right now because we got 2 minutes, but I encourage you guys to open up the scene and kind of trace those steps and see if you can come up with that on your own this week, okay? Because we're going to spray paint the wall next week, among other things. Probably break it too. Yeah. So let me show you how to put the color on. Okay, so I've got all these points, and right now they're black. They don't have a color really. Okay. Now, here we're going to put a random color on these points. So I've used a ramp for that. Now, ramps are a very cool and powerful way to control color. It's much better than expressions and things like that, random expressions. So instead of randomly choosing a color or using a switch between a very limited amount of colors, say I wanted I wanted most of the bricks to be red. So I want this amount of bricks to be red, and then I want the remaining percentage to be anywhere from dark gray to white. So you can see where ramps are very useful for that, because now I have very finite control over the percentage, and I can do smooth transitions. So I want mostly gray, I go over here. I want mostly red, I go over here. Okay? We can see that manifesting itself in the system. Here's mostly gray. Here's mostly red. I had to do this with the Invictus crowds and control how many like what color their garments were, hairstyles and stuff like that, male female distribution, that kind of thing. Just using a ramp in Houdini. Okay. So all right. So how do you use this funky ramp? So over here, I'm referencing the ramp in the color, but I'm not using a random in the way that we already did. I'm using a random expression, but it's to choose a position on the ramp. Okay, so first I'll make the ramp. Let's just do that. So new points up. Okay. And here's the parameters up here. Notice it doesn't have a ramp, so it means I have to add one. Alright, so I'm going to get a color ramp. What did I just do? Right click, edit parameter interface. Okay, so you can add whatever parameters you think you might need. Okay. There it goes. Okay, so I'm going to drag over a ramp into my parameters. I'll call this brick color. Brick. Okay. And if I hit accept, then a ramp will appear up there. There we go. Okay. Now, this isn't being used for anything yet, so if I do this, I can do this all day long. It's not going to do anything. All right. But if I reference this ramp, I can use my point number to reference that ramp. Okay. So I'll add my color. CH ramp. Okay, that's how to access the color on the ramp. Channel is CH, ramp is ramp. Okay, so what does it need? It needs a path to the ramp. Okay, so for this, since it's on the node itself, I don't have to do like a relative reference or anything. My relative reference would just be the name of it, so it's brick color. Okay. Then float position. Now that's important because that is the position on the ramp that each point is going to get its color. Okay, so it'd be 0 if it was at the start of the ramp. In this area, this would be 0. Way over here, this would be 1. So use my random expression to randomly pick between 0 and 1, and I would get a color out of that. So ran $PT. And I'll give it a seed. Okay? And then the last one is the index. Now, we're talking about RGB here, red, green, blue. So it has to know which color value to derive. Is it going to derive the red value of the color, the green value of the color? So logically, I want red for my red, green for my green, blue for my blue. So I'll put a 0 here for the first one, which is red. All right, and that's my expression. So I'm just going to copy and paste this expression to the green and switch this to 1. Copy and paste this to the blue, switch this to 2. All right, and now I've gotten the values out of my color ramp. Change to red. There we go. Okay. So that's how I use this color. Now, if you just plug this into a copy, it's not really going to do anything. See, it's going to make the bricks, but they don't have color on the brick itself, so it's not going to really do anything with that color information that we just put on those points. If you want to do the color information, it's not the first tab, not the second tab, it's way over here, third tab, use template point attributes. So the template is this side, template to copy to. So the point attribute on the template would be CD for color. So by using that, I think it defaults to star to use everything. We don't want it to use the normals. We put those normals on our line, and now it did all kinds of weird stuff with our copy. We don't want that. So instead of star for everything, I'm just going to use CD for color. All right. Now we can control the color of our bricks by a much more powerful method than switching between different bricks. Okay. So that is what I would consider, it's not that many nodes. That would be more of a professional application of the techniques you learned today. All right, so yeah, try to dissect it this week and email me if you have questions, run into problems, and try to help. So, overall, Houdini, effects, questions. Now is the time for questions. What do you guys got?
Can you explain the flow again?
The what?
The flow parameter?
Sorry, I didn't understand the flow.
Yeah, in the expression.
How do you
Usually
break
it's
it
a
up?
parameter,
How do you break the line up and down?
Oh. Okay. Yeah, the normals. Yeah. So basically, with the sort, we need to. Here's the point numbers. Okay, and then we need to figure out how to get our normals, which is the direction it's pointed essentially, to go from one point to the next point. And that's not really an easy task, actually. So to do that, the simplest way I could come up with was to, now I'm sure there's other ways to do it as well, but the simplest way I could come up with was to resort those point orders. So I offset the point orders by 1. Okay, so imagine the line, and you're just offsetting that. And now the points are going to point to their neighbor. Okay, so watch the point numbers change as that happens. Okay, so the expression here I use to do that is an if statement. If statements are used a lot in programming. It's a condition that says if it's one way, do a certain thing. If it's not, do a different thing. Okay, so the condition I gave it is if the point number is 0, which meaning if it's the first point. So in this case, when it goes to find the first point, it's gonna get this guy. It's gonna test true for this one. Okay. If its point number is 0, set it to 10,000. Okay. Otherwise, don't. Okay. So here it set it to whatever that was, a big number, and then I'm using point number plus 1 for the rest of them. And what that means is this is now going to be offset by 1. Okay. Now, the reason this is so big is because I wanted to make sure that it was enough for the whole line. If I wanted to be procedural about this, I could do the total number of points plus, let's see, just like a number, and then it'll get the same result. Okay, so this will go to a big number, and then it'll offset the rest of the points. Does that kind of make sense? So then when I do the flow, as we call it, normals are going to, using like tx2 minus tx, ty2 minus ty, getting those vectors going into the first input here, second input here, it's going to point at its neighbor. All right. This is a bit advanced, okay? Like, I'm not sure how many minutes it would take an FXTD studio to come up with that. I think it probably would take them about 10 minutes, okay, to come up with a way to do it like that. So, I can see where this would be kind of confusing. This is hard. Don't worry about understanding it all right away. Okay. Does that make a little more sense, or is it more confusing? A little more sense. Okay. You'll come up with these ideas as you progress more in the program. Like the reason that I'm trying to teach very basic nodes instead of like the shelf tools. Like we could jump into doing dynamics right now if we want. We can just drop in a box and break it and stuff. But the reason you have to know this stuff is exactly for these kind of situations where you're given a very abstract guidelines to do your effect with, and you're like, how do I do this? And if we don't have problem solving skills and basic foundation of the program, we won't be able to do it. All right.